Welcome to This Explainer. Today, we're diving into a highly conceptual but honestly fascinating framework for the future of artificial intelligence. It's called the energetic paradigm. Over the last several years, modern deep learning has achieved absolutely remarkable progress, and a lot of that has been driven by massive datasets and sheer computational scale. But as these systems become more deeply embedded in our daily workflows, new questions are popping up. Questions about structural organization, resource use, and long-term sustainable development. Today, we're going to look at the energetic paradigm not as some replacement for deep learning, but as a really thoughtful, complementary perspective, one that encourages us to build more efficient, transparent, and responsible AI systems by completely rethinking how we value the human knowledge that actually fuels them. So let's take a calm, academic look at how this all works. Okay, let's dive right into our roadmap for today. We'll be rethinking AI progress, tackling the knowledge depletion problem, unpacking the energetic paradigm itself, looking at structured knowledge recirculation, and finally, figuring out how we actually measure sustainable intelligence. So, to set the stage, we really need to contrast two different perspectives. Right now, we're in what we might call the scale-driven AI era. Progress here is mostly defined by growing network structures, cranking up computational scale, and higher resource consumption. And crucially, success is usually evaluated by task substitution, essentially asking, can the AI do the job of a human? But the energetic paradigm perspective shifts his focus entirely. Instead of just looking at raw scale, it focuses on organized information flows and coherent internal representations. It advocates for balanced resource utilization and evaluates success based on sustainable intelligence. It asks not just if an AI can perform a task today, but how efficiently its internal structures are organized to maintain that capability over time. All right, Section 1, Rethinking AI Progress, and specifically the limits of scale. As we just mentioned, current AI automation is almost exclusively evaluated through the lens of substitution. It's a natural framing, right? We want to know how many human tasks a model can take over. And to be fair, for narrow, static tasks, this framework works perfectly well. If a task literally never changes, a machine can just substitute the human effort indefinitely. But the reality of complex enterprise environments is that tasks aren't static. They are highly dynamic. Knowledge-intensive organizations are constantly shifting, and that requires ongoing edge case reasoning, maintenance signals, and deep human judgment. When we only measure an AI by its ability to substitute labor, we completely miss the dynamic dependency it has on the human workers who are continuously updating and correcting the system's operating environment. Let's move to Section 2 and see how this builds into the knowledge depletion problem, or the hidden cost of extraction. This brings us to a really critical concept, the knowledge source depletion problem. By definition, this occurs when a system converts human input into AI capability, but then completely fails to recirculate value back into the human capacity that generates future knowledge. Think about software engineers generating bug reports or operations staff writing up incident playbooks. Those artifacts aren't just byproducts of labor, they are the renewable knowledge flow that keeps automated systems actually useful as the real world changes around them. If an AI just absorbs this knowledge, but the organization simultaneously weakens the human workforce's capacity to regenerate it, say by reducing their roles, cutting training time, or stripping away authority, well, the source of the AI's intelligence actually begins to dry up. So the crucial point here is captured perfectly in the source paper. It states that enterprise AI systems can consume their own knowledge source. The system may improve in the short horizon while increasing long-run brittleness. This is a profound systems problem. It basically means an organization might see massive short-term productivity spikes as the AI automates tasks based on existing human expertise. But over the long haul, as the environment inevitably changes and those human experts are no longer around to provide tacit context and corrections, the AI's performance becomes incredibly fragile and brittle. It's an extractive model that ultimately destabilizes itself. Moving on to Section 3, the energetic paradigm, where we start viewing human work as a renewable source. The energetic paradigm really starts with a simple, kind of profound question. What flows actually sustain a system? In a knowledge organization, those flows are attention, judgment, correction, memory, exception handling, and responsibility. The framework calls these energetic flows because they require active, living effort. They are eventually transformed into durable, structured artifacts, like safety constraints, code review comments, and design principles. The paradigm argues that human work is not merely a financial cost that needs to be eliminated. It's a vital, energetic source. And any automation is only sustainable if it doesn't destroy this source faster than it can be regenerated. Okay, Section 4. Structured knowledge recirculation, or transforming these human corrections into reusable assets. Think about when a human corrects an AI. We can't just toss that raw text into a database and hope this system figures it out. Raw retrieval of unstructured text often leads to the AI applying rules totally out of context. Instead, human corrections need to be converted into structured knowledge objects. A proper knowledge object includes the specific context of where a rule applies, a compressed reusable rule, the risk type, and critically, a boundary condition, which explicitly tells the AI when not to apply the rule. It also includes a future test heuristic to detect if that specific error happens again. By structuring human feedback this way, we turn a fleeting correction into a durable, auditable asset that the AI can reliably use without overgeneralizing. Now, what's really interesting here is the concept of energetic knowledge recirculation, or EKR for short. This isn't just about updating the AI, it's a closed loop. It mandates that the value created from this structured human knowledge must be routed back into the workforce. This could mean reinvesting in human expertise, expanding worker authority over workflow design, or completely transforming their roles. Without this return channel, knowledge capture is simply extraction. EKR is the crucial feedback loop that ensures the human knowledge source remains robust, so it can continually generate the high-level judgment the AI relies upon. Which brings us to our final section, Section 5, Measuring Sustainable Intelligence Using the EKR Bench-Gated Protocol. So, to measure this properly, we first have to understand why standard, single-number leaderboards just don't cut it. They fail because they collapse multiple, totally different failure modes into a single score. Imagine an AI system is asked to fix a piece of code based on a past human correction. The AI might perfectly understand the logic and generate the correct fix, but it might format the text slightly wrong, or the test environment itself might be broken. A standard leaderboard just marks this as a 0 for intelligence. That completely confounds a minor formatting issue with a total failure in reasoning. We just end up with a totally uninterpretable metric. To fix this mess, EKR Bench proposes a really strict 6-step gated protocol, and the AI has to pass each gate sequentially. Gate 1 ensures the AI has enough context, but no cheating, so no leaked answers. Gate 2 is grounding. The AI must correctly identify exactly where in the code the edit belongs. Gate 3 checks applicability. Does the proposed fix actually apply to the file without breaking the structure? Gate 4 is a smoke test to ensure the code still compiles. Gate 5 verifies that the test environment itself is actually functioning. And only if the AI passes all 5 of these gates do we reach Gate 6, correctness, where we check if the bug was actually fixed. This gated structure prevents us from confusing an AI's reasoning failure with a simple, silly environment glitch. And this brilliantly illustrates exactly why structuring our inputs and outputs is an absolute game changer. During a pilot validation on real software tasks, the researchers tested how well the AI could ground its answers, meaning could it find the exact place to make an edit. When they let the AI output naive, free-form text diffs, it only succeeded 16.7% of the time. It failed mostly due to syntax and formatting errors, not reasoning. But when they required the AI to use structured exact edit intent, breaking down its answer into specific structured fields, the exact grounding rate jumped to 60%. This absolutely proves that unstructured prior text is a terrible way to evaluate AI. Structured, auditable knowledge loops vastly improve performance. And it gets better. When the evaluators allowed for slightly fuzzy assisted grounding, meaning the AI found the semantic intent even if, say, a comma or space was slightly off, applicability absolutely skyrocketed to 80%. All of those patch candidates successfully applied to the codebase. This provides really strong empirical backing that when we use the structured knowledge objects proposed by the energetic paradigm, the AI's ability to actually utilize human corrections increases dramatically. Now, you might be wondering, what about that final gate, full correctness? Well, full correctness actually wasn't reported in the pilot. Why? Because of historical repository environment incompatibilities. For example, outdated Python versions in the historical code repositories simply block the test from running locally. A lesser benchmark would have just marked all these AI attempts as failures. But because EKR Bench uses this gated protocol, hitting this wall actually proves the necessity of having a separate environment gate. It shows exactly where the breakdown happened, preventing researchers from falsely claiming the AI lacks intelligence, when in reality the testing environment itself was just fundamentally incompatible. So let's pull all of this together with some core takeaways for the future of AI. First off, accuracy alone just doesn't describe a system's true quality. We have to look at how sustainably that accuracy is maintained. Second, progress has to evolve beyond purely scale-driven extraction, where we just throw more compute at a problem while depleting the human expertise that actually guides it. Third, moving forward, we must measure AI by its coherence, its structural organization, and its resource consciousness. And finally, robust human AI workflows absolutely require structured, auditable knowledge loops, like energetic knowledge recirculation, to remain stable over time. I want to leave you with a final, pretty provocative question. As we deploy these increasingly powerful models into our organizations and societies, we face a fundamental choice. Will our AI systems act as extractive engines that deplete the very human intelligence that created and maintains them? Or can we embrace frameworks that the energetic paradigm to build systems that sustainably regenerate and elevate human expertise? The structural choices we make today will answer that question. Thank you for joining me for this explainer, and keep questioning the structures behind the technology we use.